I'm good at this.
Hey, what's up?
Oh, you want to be CC'd in the email that I'm gonna send out with the video recording and
Sure. Yeah.
the Venn diagrams and everything on the
Sure.
plans?
Yeah.
So just want to make sure I'm gonna watch this recording. I have to finish some things for SES for formula.
Okay.
So I'm gonna watch the recording. You also post your notes, correct?
Yes. Yeah.
Okay. So I'll download your notes, follow through it. Thank you.
Yeah.
And
Yeah.
I do.
Yeah.
I was looking through and I'm like, I was like, five mesh iron done.
You did.
Convergence.
But I have not done that, but for some reason I have the business tag. I can do the business team, which I don't know. I probably can, but I'm not in there. That's fine. It's probably why I haven't been able to see all that like for that stuff. It still explains it.
You get to see all the finances.
Yeah, that's it though.
We'll make sure to message the underclassmen chat.
Okay.
Well,
Yeah, no.
just say
I can also see the arrow sub.
Close del G.
I don't know if you have.
2025 lots,
Um,
or is it just arrow?
it just says arrow.
It's not us. We have a separate lot line.
Damn.
like.
Yeah, I can see the flash. But I can see underground.
We open all the previous years. Yes. But yeah, either way, send me a direct message. I kind of don't want to announce it in the other classroom chat because then everyone's gonna show up.
Right.
And I kind of don't want to get crowded.
Okay, I'll send you the email.
Either way, today was very much a trial run. We were supposed to start at 10. Well, we were supposed to start at 11. We realized we still need to do it until it got to 12. And at 12, we went to lunch. We started at 1.
And then you start at 2.
No, we finished at 2. So we
Okay,
finished
it
around.
didn't continue, it
we
didn't
finished-
snowball more.
We finished around 2:50.
Okay.
It's just, we learned all the prep.
Okay.
Have a good night, Professor.
Thanks, you too.
I'd give you a handshake, but my arms are itchy, which means probably carbon.
Okay.
Take care.
It looks like a top hat. So we see. It's not for the most part, and we can avoid the hole. Yeah, this is the Rizzler and cost of that. I see you found. But I feel like out of bounce. I thought you see top of that. Where did cost of that? It's not. No. Yeah. They're gonna draw a line on them. Oh, line on us? Yeah. Yeah. Oh, yeah, their stance or whatever. Just. Get up from. On that line. But then.
Can't believe.
Yeah, dude, we're gonna get that. Yeah, we. Better than.
Yeah, the world.
They got the design.
Right.
You didn't know.
I almost started walking to the other classroom. The control system was loud. Running autopilot. Oh, me. And it says I woke up early today because I had to meet with the pantry. Like lower conceptual design and shit. Yeah.
I didn't know that. The bell. So.
Wait.
Yeah, I was walking. I went to push the door open, but that shit didn't budge. It was like. I just fucking not make so. It actually was fucking too. Like so many people behind me. I was like, yo, I didn't know you were just walk away.
Oh,
I was like, "Shit."
wait, which one was
You know that one sensor door to automatic.
that? Yeah.
It was the door right there.
Oh, it was walking down.
I guess so. I tried to read it and that shit didn't budge.
Oh.
It was like a wall. It's like, look, it looks like shit down.
On forever. No, it's just nice.
It's easy to fix.
No.
So tiny.
So my brother like used my computer and then when he left to go to sleep, I went into my room and there's just Cheetos on it. And I was like, what the fuck? At least vacuum it or some shit. I don't know.
That's.
So I changed my computer. I was like,
Is losing it?
They had.
Okay, it's 5:30. Let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Good, hanging in there. It's week 11. It's the time when, I'm feeling pretty tired. Okay, but we must march on. So today, we're gonna finish up our lecture notes on beam elements. So hopefully everyone got my email today. I'm pivoting a little bit. Just because I want to make sure that we have enough time to talk about transient simulations. So our next ANSYS activity is going to be next Thursday, actually. So I want to make sure that we have enough time to talk about all of the prerequisite information before that. So I'm cutting the beam element segment a little bit short. So the plan for today is we're just going to finish up that example that we started on Tuesday, and then we're going to jump straight into transient simulations. Okay, so some announcements, and so, I did have to make an adjustment to the problem set, and so, if you look at problem 4B, the previous problem 4B, it was about distributed loading. And so I've since kind of removed that problem and replaced it with another one. And so make sure if you're doing the homework, make sure you download the latest version of the problem set to use, for, okay? All right, any questions I can answer before we get started for today? Okay, All right, so let's go ahead and pick up where we left off. So actually, let me go ahead and scroll up. Just so you can look at the problem that we were looking on before, okay? So last time we were here on Tuesday, we were working on this beam problem. So you can see here we have two beams, beams A and B, and they're being supported by a spring on the right. Okay? So this is a combination of beam and spring elements in the same problem. So we were working through this problem, and so we computed the element stiffness matrices for each element, and so that includes the two beams. Okay. And the spring, okay? So for the spring, we did something a little bit special where, you know, even though it's technically a two-dimensional spring, because that spring is rotated upwards, we saw that, you know, we have no, you know, there's no reason for us to keep the x deformations in our spring equations, okay? So we basically removed them, and we ended up with this element stiffness matrix here, where we have k times 1 minus 1 minus 1, 1, times the two y direction deformations, d3y and d4y. Okay. And so the last thing we did was we input these into our stiffness matrix here. Okay. So we included the element stiffness matrices for our two beams, element A and element B in orange and green. And then our spring we input in purple down in the bottom. Okay. Now remember the key point here is that, you know, because the constant out in front of the spring element stiffness matrix is different than the beams, we just need to make sure that we account for that when we add these into our equation here. Okay. Okay, so that's where we left off. Let me go ahead and fill in all of the blank spaces too with zeros. Okay. All right, so there is our fully assembled, you know, global stiffness matrix. Okay. So the next thing we need to do here is we need to apply our boundary conditions. And so we had two constraints and one load here. Okay. So we go back up to the figure. We can see that we have a fixed support on node 1. Okay. We have a fixed support on node 4. Okay. So those are our two constraints. So let's go ahead and apply these first to our global matrix. Okay, so fixed support on node 1 means that we're going to cancel out both of the degrees of freedom at node 1. Okay, so that means d1y and theta 1. Okay, so let's go ahead and clear those out. So that means this first row here and the second row. All right, so let's do what we usually do when we have constraint type boundary conditions. Let's replace the entire row. And so we're going to have zeros in every single entry except for the diagonal entry. So that means for the first row here, we have 1, 0, 0, 0, 0, 0, 0. And then on the right hand side, instead of f1y, we're going to replace that with a 0. Okay. And then in the second row, we have 0, 1, 0, 0, 0, 0, 0, and then we replace m1 with a 0. Okay. All right, so same as we always do. Okay. All right, the other constraint type boundary condition that we had was on node 4. Now we only have one row here that corresponds to node 4 because it was only attached to the spring. So that's going to be the last row in the matrix. Okay, so once again, we're going to replace everything with zeros here. The only one that's going to be non-zero is going to be the diagonal entry, which for the last row is going to be the last column. And we're going to put a 0 in the right-hand side. Okay, good. So our constraints are taken care of now. Next thing we need to do is to incorporate our load. And so we go back up to the problem. We can see that we have only one load applied on this figure, which is a load of 50 kilonewtons applied in the negative y direction on node 3. Okay. And so we go to the row here that corresponds to the y direction on node 3, and so that is the what number? 1, 2, 3, 4, 5th row. Okay. Right, and so since it's a load type boundary condition, we're only going to place the load in the right-hand side vector. And so we have a load of minus p over there. And then everything else, because we don't have any other loads, we're just going to replace everything on the right-hand side vector with zeros. Okay. All right. So we finally have our linear system here. And so let's go ahead and solve it. And so, we actually have numbers here that we can plug in. And so just to remind you, the numbers for this problem are, we have a Young's modulus of 210 megapascal, a moment of inertia of 2 times 10 to the minus 4. For the spring, we have a spring constant of 200 kilonewtons per meter, and the length is 3 meters. Okay. And so we plug all those in as well as the value for the load. And I was not smart about this, so I didn't leave room for it. So let me go ahead and write the answers down here. And so we plug all these into MATLAB, and what we get is. Okay, so we have first we have the deformation and the rotation at node 1. So we have d1y theta 1. Remember, node 1 was fixed to the wall, and so these should give us 0. When you solve for the rotations and beam problems, usually they're given in units of radians, okay, which is technically unitless. But there is a difference. There is a difference when you express angles in radians versus expressing angles in degrees. Okay. Okay. Next, we have the deformations and rotations at node 2. So this is the node in between our two beams. Okay. And so we plug into MATLAB, and what we get is d2 is minus 0.02 meters. Okay. And the rotation here is a minus 0.012 radians. Okay, then we have the same solution at node 3. So for node 3, we have a deformation of minus 0.0638 meters. Okay. And then theta 3 here is a minus. We have a minus 0.016 radians. Okay, and then finally we have d4y, node 4 with the only node that's attached to the spring. It's also attached to the ground. And so we end up with a vertical deformation of 0 for node 4. Okay. So of course, getting these numbers, it's almost a little bit meaningless to go over this in the lecture, just because it's all about plugging into this matrix here, putting in MATLAB, and you somehow get this. Okay, but in case you want to kind of run through the problem yourself and make sure that you got the right answer, you got the right matrix, then this is the result here. Okay. By the way, so people have asked me, how is the midterm exam going to be like? So of course, you're not going to be able to use MATLAB on the exam, and so I'm not going to expect you guys to basically compute solutions like this. I know some graphing calculators are able to solve linear systems, but not everyone has a graphing calculator like that. And so for the exam, My only expectation is that you're able to kind of get to this point right here, okay? So you should be able to define the global stiffness matrix. Actually, you should take it one step further than this. So you should at least plug in for all the values here, okay? And so if you're able to show me the global stiffness matrix with all the appropriate values and all of the boundary conditions kind of properly fitted in, you know, that's what I'm gonna ask you on the exam, okay? All right, any questions on this? Okay, good. All right, so one last point before we kind of move on from direct stiffness is this idea of computing reaction forces. Okay. So what are reaction forces? And so reaction forces are, you know, forces that are placed on your model that are not explicitly external loads. Okay. And so another way to put this is that, you know, in order for your structures here to achieve static equilibrium, right? What do we know about static equilibrium? We know static equilibrium exists when the sum of all the forces on a model equals 0. Okay. That's kind of the first thing that you're taught in kind of, you know, introductory physics. Okay, so all the structure that we're considering are in static equilibrium, but we kind of enforce it in kind of a slightly different way. And so what we're saying here is that, you know, for our finite element problems, the way that we enforce static equilibrium is by, you know, enforcing these constraints, right? So we have our fixed supports, we have our roller supports and pin supports. Okay, in reality, you know, these supports or these constraints, they have to exert forces on the model in order to maintain static equilibrium. And so these forces that are applied at our constraints, we call these reaction forces, okay? Because these are forces that are exerted in reaction to, you know, other external loads, okay? It's the same thing, you know, with us, right? And so, you know, just by sitting in this room, just by standing in this room, right? Your body is mostly in static equilibrium, right? No one is shooting across the room at you know, at 50 miles an hour, right? Kind of, you know, sitting peacefully in this room. And so, you know, there is a constant force of gravity that's being applied on us. And so to maintain static equilibrium, the ground has to exert an equal and opposite reaction force upwards. You know, that's basically Newton's third law. Sometimes it might be useful in finite elements to compute what these reaction forces are, you know, just so that you can kind of, you know, better understand which of your constraints is kind of doing most of the work in terms of maintaining equilibrium. Because oftentimes, it happens when you have a structure, one of the more common places for a structure to fail is around where, you have these constraints, right? So it's on the location where you apply the bolts, right? It's on the location where you apply kind of fixed support, right? And so knowing which of your constraints are kind of exerting the most force, it can kind of give you a hint in terms of where, maybe you can stabilize your structure a bit better. So we can compute reaction forces in finite elements. In fact, we can compute them in direct stiffness. We just have to do them in a very unique way. Okay, so to compute reaction forces in direct stiffness problems, what you want to do, so this is something that you have to do after the problem is done. So if you think back to how we computed stresses in truss elements, it was very similar. And so we have to kind of wait until we obtain the deformation solution. And so what you're going to do is you're going to multiply the deformation solution you're going to multiply that by the global stiffness matrix. Okay. But you're not going to multiply it by your final global stiffness matrix. Okay. You're going to multiply it by the global stiffness matrix that you had before you applied the boundary conditions. And so if you think back to our direct stiffness methodology, so step one of our direct stiffness methodology is to write out the element stiffness matrices for all the elements. Step two is to assemble that into the global stiffness matrix. And then step three is to apply the boundary conditions. Okay. So in between step two and step three, we had a global stiffness matrix. Granted, it wasn't one that we could solve, but we had one that we can use for this step. Okay. So for example, for the last problem, let me go ahead and write out our global stiffness matrix again, but before we apply the boundary conditions. Okay. So if you look back at the previous problem, this matrix that I had here, was our matrix after we applied the boundary conditions. Okay. But actually, if you're watching this on YouTube later, if you rewind to the beginning of the lecture and you saw what the global stiffness matrix looked like, that was the matrix that we wanted. Okay. Okay, and so if we write out that matrix again, we get EI L cubed multiplied by. We had a 7x7 matrix. We had 12, 6L, minus 12, 6L, 0, 0, 0. Okay. So that was the first row of the matrix. Second row is 6L, 4L squared, 2L, 6L, 2L squared, 0, 0, 0. Next row is minus 12, minus 6L, 24, 0, minus 12, 6L, 0, 6L, 2L squared, 0, 8L squared, 6L, 2L squared, 0, 0, 0, minus 12, 6L. Now we have this weird term here that has our spring constant. We have 12 plus K L cubed over E I. Minus 6L. K L cubed over E I. Next row 0, 0. 6L. 2L squared. 6L. 4L squared. 0. I know this is painful. Usually we don't do this, but because I didn't have the foresight to do this, and so I just applied the boundary conditions straight on the matrix from earlier. So this was a consequence of my own demise. All right, but we're on the last row. Last row is probably the easiest. So it's mostly zeros here. We have minus K L cubed over EI. 0, and then positive KL cubed EI. Okay. So this right here, this is our original global stiffness matrix. Okay. This is the one that we had before we applied boundary conditions. All right, so we're going to take this matrix and we're going to multiply it by our deformation solution. So the solution that we got at the end of the last example. Okay, we're going to multiply it by a vector here, and of course you would probably perform this multiplication in MATLAB. You multiply by d1y, theta 1, d2y, theta 2, d3y, theta 3, d4. Okay, but unlike in the previous problem, we actually have values for all of these because we already solved. Okay, so we're just going to plug in exactly what we found up here into this vector. All right, so for d1y we have 0, theta 1 we have 0, d2y we have a minus 0.02, theta 2 is a minus 0.012, d3y is a minus 0.0638, theta 3 is a minus 0.016, and d4y is 0. So everything in this vector here, this is our deformation solution. Okay. And so if we perform this matrix vector multiplication, we end up with the following. Okay. And so we have a 7 by 7 vector multiplied by a 7 by 1 or 7 by 7 matrix multiplied by a 7 by 1 vector. Okay. And so our result here is going to be 7 by 1 as well. And each entry in this vector here corresponds to a nodal force or nodal moment that's being applied on our original structure. Okay. And so this is F1y, M1, F2y, 2, F3y, 3, F4. Okay. So we perform that multiplication, we end up with the following. So what you're going to notice here is that we're going to have non-zero entries in two situations. So we're going to have non-zero entries for nodes that are applied, that have a constraint applied to them. And we're going to have non-zero entries on the nodes that already had modes on them to begin with. Okay. All right, so first we have node 1. So node 1 had a fixed support, and so we should get a non-zero entry here. So F1y is 37.0 23 kilonewtons. Okay. M1 is a minus 893.62 kilonewtons meters. Okay. Node 2 did not have any node 2 did not have any forces on it, nor did it have any constraints. And so node 2 here is I'm going to give a 0, 0. Okay. For node 3, that was where our external load was being applied. So node 3 for F3Y. F3Y we have in minus 50 kilonewtons. M3 is going to be a 0. We didn't have any moments applied on node 3. Okay. And then on node 4 was our node that was attached to the ground. It was attached to our spring. We have a 12.77 kilonewtons. Okay, and so this vector here represents the reaction forces on our structure. All right, any questions on how we got this result here? All right, so once again, the numbers here, don't really mean much just because, when I kind of jump from this step down to this step, it kind of just seems like I pull these numbers out of my, out of my butt, right? But if you actually perform the matrix vector multiplication, you end up with this metric. Okay. All right. And so with that, we are closing the chapter on the direct stiffness method. So, beyond this point, right? This is going to be the last thing that I'm going to expect you to know for the midterm exam. Okay? So midterm exam. Stops here. Okay. So I think we spent the last, 3 or 4 weeks talking about direct stiffness method. It was kind of a lot of theory and a lot at once. But now we're getting back to, I think, what everyone wants to do in this class, which is ANSYS. Okay. So from here on out, we've already kind of covered all the main basics in ANSYS, and so you guys at this point are pretty good in ANSYS. I think your guys' projects kind of demonstrated that, and so my goal with the remaining semester here is to teach you some more advanced features in ANSYS and maybe some features that you may not use every single time, but do represent really interesting and really useful features for certain situations. Okay. So I have 2 more activities planned. So I have activity 5 that's planned for next Thursday, so a week from today. And then activity 6, which is on vibration analysis, which we're going to do after Thanksgiving. Okay. But we're kind of very quickly approaching the end of the semester. Okay. Well, let's talk about activity 5. So activity 5 goes over a very kind of interesting topic. One that I honestly wish we had more time to go over because it is really useful for some situations, which is transient simulations. Okay. So what do I mean by transient simulation? So transient, the word itself means that it changes with time. So what I mean by transient FEA simulations is that these are simulations of phenomenon that naturally change with time. So these are unsteady simulations. So, I know we just got done talking about earlier today that, we usually do finite elements for static situations. Well, the world of engineering goes way beyond just static situations, right? Mechanical engineering in general is actually known for designing systems that move, right? So automobiles, airplanes, things like this nature, okay? And so you can do finite element simulations of transient simulations or transient situations. It just requires a different set of tools for it, okay? Okay. So ANSYS does have the ability to simulate dynamic situations or transient simulation or situations, okay? But one thing that you have to kind of understand before we begin is that when you're trying to simulate a dynamic situation, it's always going to be much, much more expensive than a static simulation. Okay. And we'll go over kind of the reasons for this in a bit, but just kind of intuitively, right? When you run a static simulation, right, your result is also static, right? So you can kind of capture a result with just kind of a snapshot. For a dynamic situation, right, something that changes with time, that means your results are also going to change with time as well, okay? And so instead of being a static image, the results of a dynamic simulation can be, it's not exactly like a video, but you can think of it like a video, right? So something that's changing with time. And what is the way that we often think of videos, when we're watching videos on YouTube and stuff, right? So one way that we can kind of think of videos that a video is nothing more than just a bunch of static images that we just kind of play back to back from each other very, very quickly. Okay. And so a dynamic simulation is kind of the same thing, right? And so a dynamic simulation, you can think of it as many, many static simulations that are just simulated back to back to back to back. Okay. And so, one way that you can think of a dynamic simulation is that you're running just, hundreds or thousands of static simulations, just one after the other, okay? And so that just kind of drives up the cost. So for a dynamic simulation, honestly, for the most part, you often don't really do dynamic simulations on like a desktop computer like you guys are running. Okay, you can do a fairly simple one, and for activity 5, we're going to do a fairly simple simulation of a car crash. But for anything that requires any kind of complexity or anything that requires a decent sized mesh, most of those are actually run on supercomputing clusters. Okay, actually, one of my grad students, he's just about to finish up. He ran basically unsteady simulations, on multiple different models, and we had to use a supercomputer for them. Okay. So he ran his simulations on a supercomputer which had 96 processors running in parallel to each other. Okay, so that just kind of gives you an idea of how much more powerful these, or how much more cost these simulations have compared to your static simulations on the computer. All right, any questions on this so far? Okay, good. All right, so before we get into kind of the nitty-gritty details in terms of how dynamic simulations are run, let's kind of review some stuff to give us some intuition, okay? And the intuition is going to be important for us because, you know, just like in the static simulations, you know, a big part of doing FEA is being able to interpret your results and kind of make sure and do sanity checks to make sure that your results actually make sense, okay? So the way we're going to do that for dynamics simulations is we're going to review this concept of a lump mass model. Okay. So a lumped mass model is nothing more than just a mass, a spring, and a damping constant. Okay. Okay. Don't worry, I know there's a spring, but we're not going to be doing any direct stiffness here. Okay. So there's lots of different drawings and lots of different ways to represent a lump mass model. This is just one of them. Okay. So we have our mass that's on wheels here. Okay. We have a spring constant K. This kind of strange device that I have in the bottom left, this is sometimes called a dash pot. So it has a damping constant C. Okay. And then we're pulling on the entire structure with force F. Okay. All right, so the basic idea with this is that if we pull on the structure with the force F and then release it, then this entire structure is going to oscillate back and forth. In fact, you know, you can write out the governing equation for this structure, and it's going to be a second order ordinary differential equation. Okay. Okay. I won't write out the equation just because, you know, I think that might bring out some trauma from 308s. So instead, I'll kind of show you kind of what the solution looks like. Okay. All right. And so the way that we usually describe this solution here is that we say that it is a damped oscillator. Okay. And so it's going to oscillate back and forth, but it's going to be damped. And so what that basically means is that the magnitude of the oscillations are slowly going to go down. Okay, so if we plot out the oscillations as a function of time, okay, so x, the horizontal axis here is going to be time, and then the vertical axis here will be the horizontal position of the block. Okay, so this is x as a function of t. Okay. Our plot would look something like this. So we have, you know, probably going to start with a peak. It's going to oscillate downwards. Okay. But then over time, you can see that the magnitude of this oscillation is starting to go down. So each of these oscillations here represents a vibration. But eventually it'll come to rest because of the damping in the system. Okay. All right. And so the exact solution here least a form of the solution is x of t is equal to a, where a here is the initial magnitude of the oscillation, multiplied by e minus b times t cosine of omega t plus some shift. We have a cosine term with a decaying exponential for the magnitude. Okay, so why am I bringing this up? Why are we kind of reviewing this kind of mass model? Well, when you talk about dynamic behavior of structures, you know, one of the most important properties to consider is the vibration properties of that structure. Okay. Because no matter what, you know, no matter what structure that you have, as long as it has mass, you know, if you strike it or if you kind of, you know, agitate it, it's going to have a vibratory response. Okay. And that vibration is important to analyze, you know, for resonance purposes. You want to make sure that you're not causing resonance when you load it. But it can also, you know, help to kind of understand the structure in general before. Okay. Or just in general. I mean. Okay. So nowadays, you know, vibration analysis is kind of, you know, it's not really an of course, it's not an afterthought, you know, it's an important thing, but we can understand vibration very clearly because of finite elements. Okay. And so it's not as big of an issue today, it's just because, you know, we can estimate vibration, you know, pretty accurately. Okay. But before the age of computers and before the age of finite elements, you know, engineers had to determine the vibration or the dynamic qualities of a structure, you know, without running a simulation. And the main way that engineers use to understand the dynamic properties is to relate it to this lumped mass model. All right, because the one thing about the lumped mass model, you know, we know from before that the lumped mass model kind of follows a second order ordinary differential equation, and so it's something that we can kind of directly solve, right? And so what we know about the lumped mass model is that each of the structural properties of the part can be linked to a certain behavior characteristic of the solution itself, right? And so, for example, the mass of the structure, mass will determine the structure's inertia. And what is inertia? Inertia is the resistance to changes in momentum. Okay. And so basically, the more mass something has, you know, the harder it is to get it moving, right? So we kind of intuitively know that. It's very easy to take a textbook and just yeet it across the room. But then if you took like a car, you know, if we had somehow got a car in here and we try to push it, it's a lot more difficult to push the car just because the car is a lot more massive. Okay. And so basically the higher the inertia, the higher the mass, this is going to reduce the frequency of vibration. Okay. Because a vibration is nothing more than just kind of a change in direction of the momentum. So the more mass something has, the more easily it's able to resist that change in momentum. Okay. Okay. So the next key quantity of the lump mass system is the spring constant. Okay. So the spring constant is a measure of the overall structural stiffness of the structure. Okay. So the stronger your material, the higher the Young's modulus, that's going to increase the effective spring constant of the material. There's also geometric qualities that affect the structure stiffness, so the overall length, the overall cross-sectional area. Okay. And when we link this to the lump mass model, what we see is that the spring constant has the opposite effect as the mass. Okay. Whereas the mass, if you increase the mass, it's going to reduce the frequency of vibration. Increasing the spring constant will actually increase the frequency of vibration. So the more stiffness that a structure has, the more stiffness the structure has, the more quickly it's going to vibrate. Okay. So mass and spring constant kind of have differing, kind of opposing effects. All right. So the last factor for the lump mass model is the damping constant. So the damping constant kind of has a unique effect. And so the damping constant is the only kind of aspect of the system that actually tells you how quickly the vibrations are going to damp down. Okay. Remember, from the image that we had above, eventually these vibrations are going to decay down to zero, right? It just doesn't keep oscillating forever. And so the main physical quantity that causes this decay is the damping constant. Okay. So the more damping you have in your system, the more quickly you can suppress these vibrations. Okay. Which again is a very important property, because if you have a dynamic situation, right? For the most part, you want to kind of decay the vibration down as quickly as possible. If vibrations tend to persist in your structure, you kind of have something wrong with it. Okay, so making sure there's adequate damping in a structure is something that is really important. Okay. Okay. So before the age of finite elements, what scientists and engineers had to do was they had to kind of, look at a structure, look at its kind of properties and determine, what is the effective spring constant, what's the effective damping constant. Mass is easy to determine, mass you can measure. So to predict dynamic response, okay. Sometimes it's easy to do, sometimes it's not so easy to do, because these are kind of, very simple parameters, and if you have a very complex structure, then it's very hard to do. Okay. Now, of course, with FEA, we don't have to have this task, and so we don't need to estimate these things. We just let ANSYS kind of determine them for us. Okay. But what you're going to see in that activity 5, we are going to interpret the results, right? And so we're gonna basically activity 5 is we're going to take a car, we're going to ram it against a wall, and we're going to view kind of the dynamic response within ANSYS itself. Okay. And what you're going to see is that, after the car hits the wall, there's going to be quite a bit of vibration. So there's going to be quite a bit of kind of back and forth as the car kind of eventually settles down into a static state. And so when we do activity 5, and we're looking at the results, I want you guys to kind of take a minute to actually look at the results and think about this idea of the lumped mass model. So this whole thing kind of helps to interpret results of a dynamic simulation. All right, any questions on our lumped mass model here? Okay, so before we head out for today, I did want to start the next section of these notes, which is, how do we actually go about solving these dynamic problems? Okay, so like I mentioned earlier today, that dynamic simulations, we have to use kind of a different set of tools for finite elements. Okay, so we're still going to be deriving element stiffness matrices, or at least ANSYS is going to do that. We're still going to be able to solve. But there's an additional set of parameters that we have to account for, that are unique to dynamic simulations. Okay? So let's talk about numerical solutions to dynamic problems. Okay. So, like I mentioned earlier, that dynamic problems are much more resource intensive than static problems. Okay. Instead of solving for the state of a single structure at a single point in time, you're basically simulating the response of the structure over a period of time. Okay. And so again, the analogy that I like to draw is that a static simulation. A static simulation, the results are basically like a snapshot. Okay. Whereas a dynamic simulation is, you could think of it as like a series of snapshots that are stitched together to form a video. Okay. And so each of these snapshots that make up a dynamic simulation is a separate static simulation. Okay. And so just to give you some perspective, right? And so when we think of, when we think of watching videos, we're watching movies, we're playing video games, right? Oftentimes we like to think about the frames per second in terms of, how smooth is this animation, right? And so very popular, frames per second for video games is 60 frames per second. And so what that basically means is that in the image that we're viewing, 60 frames are kind of progressing, for that 1 second, okay? And so that kind of produces a really kind of smooth kind of image for you to kind of view, okay? But if you imagine this from a finite element point of view, having 60 frames per second means that we need to run 60 different static simulations just to simulate 1 second worth of time. And so of course, it's going to take more than 1 second it's going to take more than 1 second just to run one simulation, right? And so if each of those simulations there take you, even if each simulation there takes a minute, that means to simulate 1 second of time for your structure means that it's going to take you an hour to run the entire simulation, okay? And that's not uncommon. And so, and so just to kind of give you a frame of reference, right? My grad student is simulating blood flow in the cardiovascular system, and his simulations, they only simulate about 4 seconds worth of time. So that's about 4 heartbeats. Okay. Even with like 96 processors, his simulations are taking anywhere between 6 and 8 hours to run. So he would basically upload the simulation to the cluster. He would start it. He would go to work or get a snack or something like that, or go to sleep. And then when he came back, he just kind of hopes and prays that his simulation ran just fine. And so that's kind of, you're working kind of in a very different kind of frame of reference. Okay. And so considerations for like the mesh, considerations for the computational costs, they're a lot more significant in this context. Because if you double, so let's say if you double the amount of mesh elements for a static simulation, it may not be that big a deal. Maybe your simulation takes 3 minutes to run as opposed to a minute and a half. But if you're doing a dynamic simulation where you're doing so many of these at once, that really is going to add up to a big change in the cost. Okay. So you kind of really need to be careful. And I'll stress this next week when we're doing the activity. You really want to be careful with your mesh. Otherwise you could you know. It's not the worst thing, because these computers here are pretty powerful, so, you know, it'll finish eventually. But, you know, it'll mean the difference between waiting 10 minutes for your simulation results versus waiting 10 hours. And I can't have you guys sit here for 10 hours, you know, there's another class coming in here after this. All right, any questions on that? Okay, so the next part here is going to take a little bit of time to explain. So I think we're going to call it here a little bit early today. And so when we come back for class on Tuesday, we'll go ahead and finish up these lecture notes, and that'll get us ready for the activity on Thursday. Okay. All right, so thank you guys for coming today. Hope you guys have a good long weekend. Hope you guys are able to rest up a little bit, and I will see you guys on Tuesday. Yep. You can do that. Yeah, definitely. So when you add both of these two global statements, you just end up with this anyway. So if you're kind of smart about it, so if you want to find them, you just that.
Okay, so just let's get the first one.
Yeah.
Okay.
No, nobody use the other word.
Yeah.
No, this is perfect, bro.
Yeah. No, so usually, you know, for these ones, so when you're showing kind of ANSYS figures, you know, the main thing is kind of and so usually when you have these kind of figures, you focus on whatever value that you have that you describe it. That's true.
I wanted to show you what I use for my web.
That's true, but kind of the trust that you have writing these reports, that what you write the text should be matched with that. If that basic trust isn't there,
Yeah.
you know, then we're kind of screwed.
Yeah, I was just wondering.
Yeah. It was just kind of one small, but you did really, all three of you did really well. So
Yeah.
What was it? Oh, I didn't even check the average.
I think 150.
Okay.
Yeah,
You guys did really well. So.
I had problems with the mesh converter.
Yeah, you guys kind of overkilled it for mesh conversions.
Yeah, I
talked to one of the other guys. Yeah, usually for mesh conversions, you just do for one quantity of one mesh. But you guys did it for everything,
Yeah.
which is great. I mean, which is wonderful.
But it took long.
Yeah, I know it took. I'm sure it took a really long time.
But I didn't really get the convergence that I wanted.
It's really hard.
Like this.
Yeah, it's really hard with the student version because you know you can't really push it that much.
Yeah.
But you know, because in reality, you know, even for these simple parts, your meshes are probably going to be 300, 400,000, which is impossible to use.
Yeah.
So these versions of ANSYS, they're really just kind of a teasel. They really try to force you to buy the whole thing.
Okay. Yeah.
They treat it as if it's like, you know, like goodwill, like they're trying to provide for education, but it's really just marketing so that you can buy their goodwill.
Is it really such a difference?
It is, yeah. Yeah, because the commercial one, not only there's no limit on the elements, but you can also run it in parallel too. So the ones that you're running here, it only runs on one processor, so it can be kind of slow. But for the commercial one, you can run it on 3 or 4 or 5 processors, and it just runs so much faster.
What if I, instead of like a small element that we used here, have big door, like a car door?
Take like, it's a similar.
Yeah. So in those cases, you would run it on like a supercomputer. So you run it in parallel, like you have, these supercomputers you can run up. I've seen people run simulations with up to like 1,000 processors at the same time. So for those really, really big jobs, you would run it on something like that.
Does it mean that every big company has like a supercomputer?
Not every big company, but because there's a lot of national supercomputers. So like the government, usually these things are regulated by the government. So they're usually at universities, and so they're available for kind of research use. Amazon has a lot too, so a lot of companies will use Amazon supercomputers, and you kind of run it on like a trial basis. And so you would say like, I need the supercomputer for this many hours, and then Amazon said, okay, that'll be like $1,000.
Did you ever use like a supercomputer?
Oh yeah.
Was it fun?
It's more fun in theory than it is in practice, because when you use it in practice, you're just kind of typing on the computer, and so you hit run and you think something exciting is going to happen, but you're just waiting at the computer.
Okay, yeah, okay, in theory.
It's more fun to talk about it than it is to actually use it.
Because it's called supercomputer.
Yeah,
You think like it's gonna be something special.
yeah. It's not like the movie, because in the movies you see like.
Yeah, that's.
It's not like that. Yeah.
Okay, yeah. Thank you.
Yeah, no problem.
Will you rate the homework as completed or?
Yes. Yeah, so this one too, I'll rate as completed, but then I'll post the solutions,
Okay,
so you can check your answers before the midterm.
okay, perfect. Thank you.
Yep.